Cosmic juggernauts, such as black holes that swallow everything in their path, stars that burst into violent supernova explosions, and mysterious bursts of radiation that could destroy entire worlds in an instant, are among the most extreme and devastating forces in the universe. Amidst this incredible beauty and wonder, however, lurk some of the most terrifying and dangerous objects conceivable. What happens when two supermassive black holes collide? How can a neutron star, which is smaller than a city, contain the mass of our sun and send out beams of radiation that kill everything in their path? Could there be a hidden blazer whose jets aim directly at Earth, unleashing a stream of high-energy particles that could sterilize entire regions of space? And yet within this chaos, there is also an odd equilibrium. From the explosive birth of new elements in supernovae to the enigmatic and mind-bending possibility of white holes, the time-reversing twins of black holes. Join me on this journey through the universe's most dangerous objects. We'll also learn about stellar mass black holes in binary systems, which are among the most mysterious and dangerous objects in the cosmos, as well as about supermassive black holes, the hidden predators. While supermassive black holes are the most talked about, there is another type that could be lurking much closer to Earth, stellar mass black holes. These are formed when massive stars collapse and are far more common than supermassive ones. What's even more disturbing is that many of these black holes live in binary star systems, orbiting with another star, patiently waiting for their chance to strike. Stellar mass black holes aren't always obvious. Unlike regular stars, they don't emit light. They're shrouded in darkness. And unless they're consuming matter from their companion, they can't reveal their true nature. As stars die out, the most massive ones collapse into black holes, becoming invisible predators in the system. Survivor stars, meanwhile, keep shining brightly, oblivious to the fact that their companions have evolved into something much more dangerous. Consider a scenario where a black hole begins to slowly consume its companion star. The star's gas and material are drawn in by the black hole's gravitational pull, creating a disk of matter around the black hole. This process emits intense radiation, often in the form of X-rays, which telescopes can detect. The sight of a star losing its outer layers to the greedy black hole is both fascinating and terrifying. The black hole can devour its partner over. Stellar mass black holes have been around for millions of years, transforming a once harmonious pairing into a lethal feeding ground. What makes them so terrifying is that they don't emit light unless they're actively devouring matter. Many of these black holes stay hidden, so we don't know where they are until they start eating. This raises the unsettling possibility that one of these black holes is closer to Earth than we think. Estimates suggest that there could be. There are thousands of stellar mass black holes in our galaxy, and each one could be part of a binary system. These hidden predators have the ability to do more than just devour their companions. They can also release powerful jets of energy. These jets, composed of high-energy particles, can travel great distances through space. While the idea of a black hole jet reaching Earth is implausible, it is not completely out of the question. These black holes could be peacefully drifting through the galaxy, orbiting another star, until something changes and they start feeding. Once this happens, the process could escalate quickly, leading to the black hole unleashing a torrent of energy that could have catastrophic consequences by the time we detect the threat. The radiation from these jets could cause significant damage, disrupting satellites and other space-based technology, or even endangering life on Earth. If we see warning signs like intense X-rays or a radiation jet, it might be too late to do anything. One of the most terrifying things about stellar mass black holes is how close they could be to Earth. On a cosmic scale, distances are measured in light years, and our galaxy is a huge expanse of stars, planets, and other objects. However, one of these dangerous binary systems could be hiding in what we would term our galactic backyard within a few thousand light years. Given how hard it is to detect stellar mass black holes unless they're actively feeding, it's not out of the question that one could be relatively close without our knowledge, slowly siphoning off material from its companion star. The technology we use to search for these black holes relies on detecting their effects on their surroundings. And when a black hole is drawing matter from a companion star, the material heats up as it spirals, so we can't see it. Space telescopes can detect X-rays emitted by black holes, but not all black holes are actively devouring their partners. Many lurk in the galaxy, waiting for the right conditions to surface. For the time being, astronomers must rely on sky surveys to detect these potentially dangerous objects. They must be vigilant in their search for unusual X-ray sources, as this could indicate the presence of a black hole devouring its companion star. However, the vastness of the universe and the limitations of our technology make it challenging to detect these hidden predators. Despite numerous technological advancements, our understanding of the full extent of the dangers posed by stellar mass black holes remains limited. It's unsettling to think that, as we go about our daily lives on Earth, there could be a black hole a few thousand light years away, patiently waiting for its chance to devour. There may be an infinite number of these unseen killers in the galaxy, but their destructive potential is enormous. Stellar mass black holes are smaller than the supermassive ones at the galactic centers, but they are just as terrifying for the destruction they can inflict on their surroundings. We still have a lot to learn about these black holes and the dangers they pose, but as our technology advances and we explore further into the galaxy, we may find more of them. The hunt for these black holes reminds us of the incredible dangers in the universe, which may be much closer than we ever imagined. FMY bubbles, galactic bombshells stretching tens of thousands of light years above and below the center of our galaxy, are one of the most striking and mysterious structures ever discovered. The question is, will we find them before it's too late, or are they already too close for comfort? The Milky Way is home to these enormous, highly energetic radiation bubbles that were initially discovered by NASA's Very Gamma Ray Space Telescope. Although they do not currently constitute an immediate danger, their presence does prompt inquiries into the Milky Way's history and the possibility of similar violent events occurring in the future. The size and energy of these bubbles suggest that the Milky Way's center was much more active than it is today. At the center of our galaxy, there is the supermassive black hole known as Sagittarius A, which is approximately 4 million times the mass of the Sun, is currently in a relatively quiet state. However, it continues to have a significant impact on the stars and matter in its immediate vicinity. The existence of fairy bubbles, however, suggests that Sagittarius A may have released an explosive burst of energy that sent enormous quantities of radiation into space approximately 25,000 light-years into the past. Within these bubbles, which are located on the galactic plane, is radiation of extremely high energy, including gas gamma rays, the most energetic type of light. The origin of these bubbles, if any, was an extremely powerful event that has left an indelible mark on our galaxy. What exactly caused these bubbles is still a cosmic mystery, though. Various theories have proposed explanations for their formation, the most popular of which points to the supermassive black hole at the galaxy's center, or Sagittarius A. Maybe went through a period of intense activity long ago, maybe consuming a lot of gas and dust. When a black hole eats, some of the material doesn't go into the event horizon. Instead, it's flung outward in powerful energy jets. One or more of these jets could have created the FMY bubbles. These explosions would have been powerful enough to send gamma rays and other high-energy particles far into space, creating the enormous structures we observe today. There's also the chance that the bubbles formed near the galactic center during star formation. This is where the galaxy's most energetic processes take place, like the rapid formation of stars. When massive stars explode as supernovae, they release enormous amounts of energy. So, maybe the creation of the FMY bubbles was a combination of star formation and supernova explosions. Who knows, maybe the fairy dust was just a coincidence. Although the exact nature of bubbles is still a mystery, scientists have determined that the Milky Way's central black hole has not always been placid and peaceful. In the past, it has been subject to violent outbursts that reshaped the galaxy's structure. The prospect that this could happen again is a frightening thought. At the moment, Sagittarius AA is relatively quiet, but black holes can be unpredictable. If the central black hole were to begin consuming massive amounts of material, it could cause another explosion that shoots high-energy particles across the galaxy, including gamma rays. In this case, the radiation could harm everything in its path, including Earth. Luckily, Earth is situated around 25,000 light-years from the galactic center, so it's somewhat protected. However, even still, the radiation from this explosion could damage satellites, power grids, and other important systems. It's quite improbable that such an occurrence will transpire anytime soon, but the fairy bubbles serve as a sobering reminder that our galaxy isn't as stable or predictable as we would want to think. What's more, the fairy bubbles appear to be a cosmic phenomenon with a relatively short age, just a few million years, compared to the galaxy itself, which is estimated to be around 136 billion years old. This implies that the event or series of events that astronomers are currently attempting to answer questions such as, is the creation of the FMY bubbles part of a regular cycle of outbursts from the galactic center? If so, could we be experiencing a period of relative calm between these explosive episodes? If so, when might the next outburst occur? This profound event occurred long after the Milky Way formed, possibly even as recently as when the ancestors of early humans were starting to walk the Earth. Scientists are still trying to piece together the full story, even with the data we have, when it comes to studying the FY bubbles. Their size and diffuse nature make it difficult to gather detailed information about their origins, and gamma rays, unlike visible light, are difficult to detect without specialized instruments like the Fairy Gamma Ray Space Telescope. Unfortunately, we don't have an answer yet. The formation of these bubbles and the information they provide regarding the Milky Way's past and future are fascinating topics to delve into. Among the most extreme and dangerous stars in the universe are Wolf-Rayet stars, which are massive and extremely unstable. As they approach the end of their lives, their final act could be incredibly violent and destructive, in contrast to the gradual fading of most stars. Wolf-Rayet stars burn brightly, furiously shedding their outer layers of. Wolf-Rayet stars are extremely dangerous because they are constantly shedding gas at extraordinary speeds, which in turn creates powerful stellar winds that push material away from the star at hundreds of kilometers per second. Wolf-Rayet stars are also among the hottest stars known, with surface temperatures that reach tens of thousands of degrees Celsius, much hotter than our own Sunday. However, the real danger comes from what happens next. These stars are essentially time bombs waiting to explode, and when they do, the resulting supernova could release an enormous starbursts, which are among the most powerful explosions known to release more energy than our sun will emit in a matter of seconds, could be unleashed during this explosion. Gamma-ray bursts, which are extremely intense, focused beams of gamma radiation that shoot out from the poles of a dying star, are among the most dangerous cosmic phenomena that could result from this explosion. Throughout its existence, a gamma-ray burst from a nearby Wolf-Rayet star has the potential to unleash a deadly beam of radiation that could reach Earth if the star's poles were to line up in just the right way. The resulting impact would be catastrophic, and the burst itself would only last a few seconds or minutes. Despite this, the radiation it releases could deplete Earth's protective ozone layer, exposing surface life to dangerous ultraviolet radiation. It's hard to predict the full impact of a gamma-ray burst, but it's clear that it would be a global disaster. Luckily, gamma-ray bursts are relatively rare, and the odds of one being aimed directly at Earth are low. However, that doesn't mean life on Earth wouldn't be vulnerable to increased radiation, potentially leading to mass extinctions. The atmosphere could also be severely damaged, altering weather patterns and disrupting ecosystems. We are completely secure. Astronomers have discovered multiple Wolf-Rayet stars in our galaxy. Although none of them are considered to be a direct threat, their existence serves as a cautionary tale about the vastness of space and the myriad mysteries it contains. One such star, WR104, is situated approximately 8,000 light-years away from Earth. As part of its binary system, WR104 is slowly orbiting another star, and as it sheds its outer layers, it forms a spiraling gas plume that envelopes the system like a cosmic dust storm. WR4 is an intriguing and potentially hazardous star because of its apparent alignment, which could cause one of its poles to point directly at Earth in the event of a supernova. This alignment raises the possibility that any gamma-ray burst from WR14 could be directed towards our direction. Scientists are currently studying the star to determine its orientation and likelihood of posing a threat, but the fact that it's even a possibility demonstrates how dangerous these stars can be. Wolf-Rayet stars are hazardous due to their enormous size and instability. These stars, which are usually 20 times the mass of the Sun, burn through their nuclear fuel at an extremely fast rate, leading to extreme instability. As a result, the star's outer layers are blown away in all directions. Eventually, the star's core will collapse under its own gravity, triggering a supernova explosion. Before their ultimate demise, stars put on a spectacular display. Their stellar winds produce massive clouds of gas and dust that can extend hundreds of thousands of kilometers. As the star continues to lose mass, it becomes encircled by a luminous, turbulence-filled shell. This process makes Wolf-Rayet stars some of the most luminous objects in the sky, visible from far away. Their intense radiation can illuminate the gas around them, forming nebulae that emit in. Wolf-Rayet stars are a reminder of the violent processes that shape the universe. Despite their stunning appearance, these stars are precursors to supernova explosions, which create the heavy elements needed for planets, stars, and life itself. The explosive deaths of massive stars like Wolf-Rayet stars are both destructive and creative, forging new materials in the fires of their demise. The universe relies on stars like these to produce new elements, but their instability makes them among the most dangerous celestial objects. It's hard to tell when a wolf star will explode. Some could go out tomorrow, while others could burn for millions of years. The mystery surrounding these stars is deepened by their unpredictability. We know they'll explode, but when exactly, astronomers will study wolf stars. Although technological advancements have made it possible to track stars more precisely, measuring their mass loss, and studying the behavior of their stellar winds, we still don't have much of a clue as to when exactly these stars will explode. What we do know is that when a Wolf-Rayet star finally explodes, it will be one of the most spectacular and violent events in stellar history. Stars like Wolf-Rayet are a testament to the incredible forces at work in the universe. They have lived fast and burned brightly, but their fiery deaths will leave a lasting impact on the galaxy. For now, they are cosmic time bombs waiting to erupt. Their fate is sealed, and when their final act arrives, it will be one of unparalleled destruction. Stars are both creators and destroyers, responsible for altering the galaxy with their explosive deaths and forging new elements. Gazing up at the stars, we can't help but wonder which of these galactic fireballs will burst next, and what will happen to the universe and ourselves when that happens. The answers might be in the far future, but for now, we must remain vigilant against the constant threat, which serves as a reminder of the delicate balance between creation and destruction in the universe. In the farthest corners of space, there is an object that has baffled scientists for decades: the Great Attractor. This gravitational anomaly is so powerful that it is attracting entire galaxies, including our own Milky Way, to it at incredible speeds. Little is known about the Great Attractor, which is hidden in an area of the sky obscured by our galaxy. Nevertheless, the undeniable pull it exerts is pulling everything in its path, including ourselves. Mysterious phenomena in contemporary astronomy. The Great Attractor is located in an area known as the Zone of Avoidance, where it is nearly impossible to observe directly due to the dense dust and stars of the Milky Way's galactic core. This obstruction makes it extremely difficult to study the Great Attractor using optical telescopes, thus concealing much of its nature. Despite this, scientists have detected its influence. Our own galaxy and the rest of the local group of galaxies are hurling toward this enigmatic region of space at speeds of millions of miles per hour, as are other methods of observation, such as radio waves and X-rays, which can cut through dust and gas. What we do know is that the Great Attractor has a tremendous gravitational force that impacts a large portion of the universe surrounding it. One of the most important questions regarding the Great Attractor is what it is. Some theories propose that it could be a supercluster of galaxies, which would explain its enormous size and mass. A collection of thousands or even millions of galaxies held together by gravity. Superclusters are among the biggest structures in the universe. One theory is that the Great Attractor is actually one of these structures that pulls galaxies in from all directions. Another is that it hides a supermassive black hole at its center, which would explain the tremendous gravitational pull we see. Black holes are known to distort space and time, so this could be another explanation. Lastly, there's always the chance that the Great Attractor is a thing that has never been seen before, something that makes us question everything we think we know about the cosmos and how everything works. The cosmos is huge and mysterious, and the Great Attractor could hold the key to unlocking some fundamental truth about reality. It's a fascinating mystery that has generated endless debate among astronomers and scientists. Regardless, we do know that our Milky Way galaxy is hurtling toward it, along with countless others. We are being pulled inexorably toward the Great Attractor at a speed of about 600 kilometers per second, a speed that is difficult for humans to fathom. As part of this cosmic migration, we will eventually reach this hidden cosmic colossus. The question is, what will happen when we get there? Will our galaxy and others eventually collide with whatever massive structure lies at its center, or will we be absorbed into its gravitational pull and lost in space? This will determine the fate of our galaxy and the entire region of the cosmos could be molded by the Great Attractor. One theory is that, as time goes on, galaxies will keep spiraling toward it, and eventually, when they collide, their stars won't smash into each other due to the vast distances between them. Instead, the merging galaxies' gravitational forces will shape them into vast elliptical galaxies, and the gas and dust within them could trigger. Cosmic collisions are causing galaxies to undergo dramatic changes and produce new stars. However, the Great Attractor isn't simply a place where galaxies meet. Its enormous gravitational pull may be part of a pattern that extends well beyond the visible universe. Some researchers even think the Great Attractor is linked to the Shapley supercluster, a space region that contains There's a huge cluster of galaxies in our local universe called the Shapley supercluster. It may be the actual source of the gravitational pull that we feel. The Great Attractor is just one piece of this vast, interconnected cosmic web. Despite how far away it seems, it still begs the question, where are we in relation to this vast, interconnected web of galaxies, all of which are affected by forces that we don't completely understand? Not fixed, but always moving, being pulled toward an unknown future, it also serves as a reminder of the vastness of the universe and how much of it is hidden from our sight as our technology advances. Astronomers keep studying the Great Attractor in the hopes of discovering its secrets. Recent breakthroughs in radio and X-ray astronomy have enabled scientists to see through the zone of avoidance, exposing galaxies and structures that were previously invisible. With any luck, we will eventually learn more about the Great Attractor and how it works. The Great Attractor is still a mystery to us, a mysterious cosmic entity from which we can't seem to break free. What's more unnerving is that we have no idea how it will influence our galaxy down the road. Granted, it will be billions of years before we witness the complete impact of our approach, but the fact that we're being pulled toward such a powerful gravitational force begs the question, what lies ahead for our Milky Way? In the far future of the universe, when all the stars have faded and the sky is black, what will remain? Will our galaxy be ripped apart by the Great Attractor's gravitational pull, or will we merge with other galaxies in a cosmic dance that reshapes the universe? These are questions that may not have answers in our lifetimes, but they remind us of how dynamic and ever-changing the universe is. Black dwarf stars are the frigid remnants of stellar death. It is believed that black dwarf stars, which are cold and dark, will be one of the last remnants of stellar life. No stars have reached this stage yet, but it will determine the fate of the universe in the long run. White dwarfs, which remain after a star has used up its nuclear fuel and shed its outer layers, are still hot and glowing objects, but they're cooling down as they release their remaining heat into space. We haven't witnessed this stage of stellar evolution yet, because the universe hasn't been around long enough for any white dwarfs to cool that much. However, in the distant future, the cosmos will be teeming with these celestial bodies that have cooled to the point where they no longer emit any detectable light or heat. At that point, they will transform into black dwarfs, which are cold and dark and blend into the backdrop of the universe. Black dwarfs are an intriguing and unsettling concept. Without light, they would be nearly impossible to spot, and their temperatures would have plummeted to almost zero, the coldest possible state of matter. In this form, they would be nothing more than a cooling ball of degenerate matter, unable to support nuclear fusion. As a result, they would no longer have any discernible impact on their environment. Eventually, all stars, no matter how big or little, will run out of fuel and die. This means that smaller stars, like our Sun, will end their lives as white dwarfs, which will cool and fade into black dwarfs. Over trillions of years, this process will continue, signaling the end of the universe as we know it, which was once filled with the brilliant light of billions of stars. In this hypothetical future, any planets that may still be orbiting black dwarfs would be frigid, lifeless wasteland without the cosmic light and heat that has illuminated the cosmos for billions of years. Any remaining civilizations or forms of life would have to find a way to adapt to this alien environment. The universe will cool down to its final state, called heat death, when all thermodynamic activity stops and there is no more usable energy. Black dwarfs play a significant role in this future, as they are among the last objects that will exist in this frozen dark universe. At this point, galaxy formation will be impossible, and space between galaxies will expand into an empty expanse. Darkness, devoid of starlight, will envelope the universe, causing it to cool and become eternally still. What's unsettling about this scenario is the thought of time passing without motion or light, and how the once brilliant black dwarfs will now lie scattered across space, motionless and silent. The galaxies that once contained these stars will have long since scattered their constituent parts. As the universe continues to expand, black dwarfs will eventually become so large that they are no longer affected by the gravitational pull of nearby stars and planets. Instead, they will exist as cold, lifeless remnants of a time when the cosmos was teeming with light. The formation of black dwarfs is a part of a grander narrative that begins with the Big Bang, when the cosmos was hot, dense, and brimming with energy, and ends with the birth of the first stars. The cosmos has always been changing, but that change is eventually leading to the end of the universe. As galaxies move farther apart and stars run out of fuel, the universe is winding down, and one last stage of that winding down is the formation of black dwarfs. When these stars finally fade away, the last remnants of stellar activity will be gone, and the cosmos may eventually reach a point where there are no stars to emit light, no supernovae to release energy, and no planets to harbor. Based on what we know about physics and cosmology, scientists predict that the universe will be a frigid, lifeless wasteland in the very distant future. This future is hard to fathom because it would be so different from the universe as we know it now, which is teeming with bright stars and galaxies. What happens to black dwarfs is also a mystery. Some think they may disintegrate over an infinitely long time, while others think they could slowly fade away. Black dwarfs represent the last chapter in the life of stars and the evolution of the universe. They are a chilling reminder of how transient everything is, and if quantum tunneling causes them to dissolve slowly, eventually, they will vanish entirely, leaving nothing behind. On the other hand, Some think that black dwarfs might persist indefinitely, remaining as the last remnants of a universe that has grown cold and dark. Whatever happens, their existence is truly remarkable. Thornsit-Cow objects TZ are among the most peculiar celestial hybrids in the cosmos. They formed during a dramatic and implausible cosmic event when a neutron star, one of the densest objects in the universe, was devastated by a supernova explosion. Now, our universe is illuminated by light, but one day, all that will remain are frigid, dark objects floating through space. Thornsit-Cow objects are extremely unusual stellar objects that form when a neutron star, the remnant from a massive star explosion, is swallowed by an older, red supergiant star. This unusual combination causes the neutron star's dense core to sit inside the supergiant's bloated outer layers, creating a star that operates under completely different physical conditions than any regular star. To fully grasp the peculiarity of these objects, it's helpful to examine the two components that make them up. In contrast, red supergiants are massive stars that are almost dead. They've blown up to many times their original size, with their outer layers blown out into space as they use up all of their nuclear fuel. A teaspoon of neutron star material would weigh billions of tons on Earth. Their gravitational pull is tremendous, and they can spin quickly, emitting powerful magnetic fields and radiation beams. In an unusual twist on stellar evolution, a neutron star that has been ejected from its original supernova, instead of being destroyed, sinks into the core of the red supergiant and becomes the new center of the hybrid star. The red supergiant's outer layers keep functioning as usual, fusing elements in nuclear reactions, but with the neutron star inside, everything changes. In a Thorn-Zito object, the physics are entirely different from a regular star. Instead of hot, dense gas undergoing fusion, the core is now a superdense neutron star. This changes the star's behavior in some unusual ways. For example, the outer layers of the red supergiant could act unexpectedly due to the neutron star's immense gravitational pull. In a regular red supergiant, the outer layers are relatively stable, but in a TZ, they could undergo sudden and violent shifts. The presence of a neutron star could trigger outbursts. Thornsit-Cow objects are known to erupt with unpredictable behavior, sending material hurtling into space at high speeds. If one were to exist near our solar system, the radiation it released or the shock waves it caused could pose a significant threat. The effects of such an outburst could be felt on Earth, disrupting communications and satellites, and possibly causing damage. The presence of a neutron star inside the red supergiant could cause unusual gravitational and magnetic effects. Neutron stars already have some of the strongest magnetic fields in the universe, and when combined with the massive outer layers of a red supergiant, these fields could behave in ways we don't fully understand. The hybrid star could act like a giant, adding even more danger to any nearby systems. Additionally, the magnetic field surrounding a TZ could be extremely powerful. The neutron star's gravitational pull and the mass of the red supergiant could cause space to warp in unpredictable ways. The fact that only one potential candidate for it a star called HV 2112 in the small Magellanic Cloud, has been observed adds to the mystery surrounding these objects. Their intense magnetic fields extend across space and could interact with nearby stars or planets, altering their magnetic environments. HV 2112 is still being debated as a possible Thornsit-Cow object, and scientists are still trying to determine if it is indeed one. The formation of TZs is extremely rare and requires extremely specific conditions. For example, a neutron star must survive its supernova and then encounter a red supergiant in such a way that the merger can only happen under extremely rare circumstances. Despite their rarity, the existence of TZs demonstrates how diverse and stellar evolution can take strange and unexpected turns, as TZ reminds us. A neutron star and a red supergiant forming one is a cosmic oddity that doesn't fit neatly into our normal understanding of star life and death. The potential instability of Thornsit-Cow objects is another reminder of how unpredictable the universe can be. Traditional wisdom holds that stars are massive balls of hot gas that burn brightly for millions or billions of years before eventually exploding. Stars, contrary to popular belief, are not static entities but can, in fact, undergo rapid and violent metamorphoses in response to perturbations in their local stellar environments. This instability has the potential to make TZ objects among the most hazardous in space, particularly in areas where other stars or planets are located. The fate of TZ objects is also uncertain due to the peculiarities of these stars. The exact duration of their hybrid state remains unknown, although some scientists speculate that TZ may collapse into a neutron star, causing a supernova-like explosion. In such an event, the hybrid star could disintegrate, releasing massive quantities of material into space. This kind of explosion is comparable to a conventional supernova, but with the added twist of the neutron star's involvement, which could result in even more catastrophic consequences. TZs can have far-reaching effects on the surrounding space, and the presence of neutron stars in their cores begs the question: what happens when a red supergiant's outer layers are stripped away by stellar winds? As red supergiants cool down, they lose mass, and if the neutron star is stable, a Thornsitt-Cow object could eventually strip away the red giant's outer layers, leaving behind just the neutron star and a cloud of material. A star's instability could set off a chain reaction that destroys the star entirely. Supermassive black hole mergers are among the most spectacular and violent cosmic events, but they take a very long time to occur, millions or even billions of years. At the center of many galaxies is something even more dramatic: a supermassive black hole. When two galaxies merge, their central black holes are pulled toward each other and eventually combine into one. When two black holes collide, it causes a tremendous explosion that is both terrifying and fascinating: a supermassive black hole merger. These collisions are so enormous that they could cause ripples in space-time, and the energy released in the form of gravitational waves traveled through space at the speed of light, which were initially detected by a cosmic event that reshapes the surrounding galaxy. Supermassive black holes are enormous, powerful objects with masses millions or even billions of times greater than our suns. Their gravitational pull is so strong that not even light can escape from them. In 2015, scientists made a breakthrough that allowed us to observe black hole mergers for the first time, though on a smaller scale than supermassive black holes. As two of these massive objects slam into each other, they unleash an immense amount of energy that defies comprehension. As the gravitational waves from the collision ripple outward, mimicking the effect of waves on a pond surface, scientists are able to detect them from Earth using sensitive instruments like Virgo and LEO, which can detect even the faintest of ripples from millions of light years away. A monstrously slow-motion catastrophe unfolds as two black holes approach each other, their immense gravitational pull distorting space-time around them. As they draw nearer to the event horizon, time slows down even more, trapping stars, gas, and dust in their path. The two black holes spiral inward, engulfing everything in their path. Eventually, they collide in a catastrophic merger, transforming into a single, even larger black hole. The energy from this merger is converted into gravitational waves as they travel through space and time, eventually settling into a new state as a supermassive black hole that has absorbed the mass and energy of its two predecessors. If Earth were close enough to one of these mergers, the gravitational forces would disrupt our solar system, and any planets or star systems in the vicinity could experience catastrophic effects. The merging black holes in our galaxy are currently not threatening to collide with any other galaxies, and our own supermassive black hole, Sagittarius A, is remaining relatively quiet. However, in the far future, the Milky Way might undergo a catastrophic event that could destabilize the planet's stable orbits around the Sun or even destroy entire star systems. Thankfully, we are not in that situation right now. The Andromeda Galaxy and the Milky Way are on track to collide, which will likely cause their central black holes to merge. This merger won't happen for another 4 or 5 billion years, but when it does, it will be one of the most spectacular events in universe history. Any sentient beings who are lucky enough to be alive to witness the collision would be in for a once-in-a-lifetime experience. The two galaxies will slowly merge into one as their black holes spiral toward each other in a slow but inevitable cosmic dance. Close observation of such a merger would be an incredible and awe-inspiring experience. The collision of two supermassive black holes is an event that surpasses our comprehension of size and power. The sky could be illuminated by bursts of light as gas and stars are dragged into the black hole's accretion disks, creating a dazzling display that would stretch and distort everything nearby. A stunning and unnerving illustration of the immense cosmic forces at work, a supermassive black hole merger has the potential to spell the end of our galaxy. The collision's forces could alter the galaxy's structure, causing planets and stars to move into different orbits or perhaps eject them from the galaxy altogether. The gravitational waves produced by the merger would travel across the universe, compressing and stretching space as they traveled through it. A supermassive black hole merger would have equally dramatic aftereffects. The newly formed black hole, now even more massive than before, would dominate the galaxy's center, its immense gravity shaping the orbits of the stars around it. Any gas or dust left in the area could be drawn into the black hole's accretion disk, where it would heat up and emit powerful X-rays as it melted. Scientists on Earth could catch a glimpse of these events billions of light years away. Supermassive black hole mergers are extremely rare on a cosmic scale, but they're happening right now somewhere in the cosmos. As the two galaxies collide, gas clouds collapse and form new stars. After some time, the galaxy would settle into a new shape, altered by the collision. It's true that we can't yet detect many of these events, but that could change as technology advances. Gravitational waves have given us a new window into the cosmos, allowing us to detect the unseen forces involved in these collisions. By studying these waves further, we can learn more about black hole mergers and what happens when two of the universe's most powerful objects collide. Mergers of supermassive black holes are an inevitable aspect of galaxy evolution. As galaxies travel through space, they occasionally collide and merge. In the end, the merger's central black holes meet, shaping the galaxy's structure and impacting star and planet formation. These mergers are among the most violent and powerful events known to science, and they serve as a reminder of There are tremendous forces at work in the universe. At present, the supermassive black holes in our galaxy in Andromeda are slowly spiraling toward a collision. This process will take billions of years, and when it finally occurs, the universe will have changed drastically. However, when that day arrives, the merging of these two black holes will be a moment of unparalleled power, shattering space-time and reshaping the galaxy. It will be the ultimate collision, the meeting point of the most powerful forces in the cosmos. White dwarf supernovae are cosmic time bombs that quietly remain after a star has used up its nuclear fuel and collapsed. Unlike more massive stars, which end their lives in supernova explosions or collapse into neutron stars and black holes, white dwarfs tend to be stable as they cool and fade into the background of the universe. However, given the correct conditions, even these dim stars can become extremely powerful. There are cosmic time bombs in the cosmos. When a white dwarf is in a binary system with a companion star, it can quietly drain its partner's mass over millennia. Eventually, the white dwarf reaches a critical mass and explodes in a spectacular type II supernova, releasing more energy in a few moments than the sun will produce in its entire lifetime. In the process of a massive star's collapse, a white dwarf, a star composed primarily of carbon and oxygen, constantly absorbs matter from nearby stars in its orbit. As time goes on, this steady flow of matter increases the white dwarf's mass. However, there is a limit beyond which the white dwarf becomes unstable. This limit is approximately 14 times the mass of our Sun. As the white dwarf gets closer to this critical mass, the pressure inside it becomes extremely intense. Type A supernovae are particularly dangerous because they can happen suddenly and without warning. A white dwarf, for example, could be slowly devouring its companion star for thousands or even millions of years before suddenly exploding. Unlike massive stars, which often exhibit symptoms of instability or swelling before their explosion, Type A supernovae are subtle but deadly threats. Final collapse white dwarfs are remarkably stable until the very moment of explosion, making them some of the most silent killers in the universe. They can suddenly burst into a supernova explosion, which can be seen from great distances, and their power is truly astounding. Its material is ejected into space at speeds of up to 300,000 kilometers per second, causing a supernova explosion. The intense radiation from the explosion can destroy any nearby planets in the system. Shock waves from the explosion sweep away any remaining gas and dust. However, the effects of a white dwarf supernova are not limited to just the immediate surroundings. The radiation released during the explosion, especially in the stratosphere, can have devastating effects on everything in The explosion wouldn't directly hurt Earth from that distance, but the intense radiation could interact with our atmosphere, damaging the ozone layer and exposing the surface to dangerous levels of ultraviolet radiation from the sun. Gamma rays and X-rays can travel vast distances, potentially affecting planets and stars far beyond the binary system. If a supernova of this type were to occur within a few thousand light years of Earth, the radiation could have serious negative consequences for our planet. Although it is highly improbable that a supernova could eradicate all forms of life on Earth, the destruction of our planet's atmosphere in its aftermath could set off a chain reaction of environmental disasters. For starters, the sun's rays could cause DNA damage, which in turn could increase mutation rates and perhaps cause mass extinctions. Additionally, the radiation could change the chemical makeup of our atmosphere, which could impact our weather patterns and temperatures. Even though it would happen thousands of light years away from Earth, the radiation fallout could be catastrophic for ecosystems and species that are particularly vulnerable to such events. Astronomers have long been interested in studying white dwarf supernovae because of their significance in measuring the expansion of the universe and their role in understanding stellar evolution. Type Ia supernovae are also known as standard candles. Type Ia supernova explosions are useful for measuring galaxy distances and tracking the expansion of the universe because their brightness is proportional to their distance. However, even though these explosions are scientifically important, they pose a threat because of their unpredictability. At this time, there are no white dwarf systems that astronomers are aware of. Supernovae of this type are relatively common in our galaxy, happening about once every few hundred years. So, it's likely that another one will happen soon when a white dwarf finally reaches the point of explosion. The exact location and timing of the next type Ia supernova explosion is difficult to predict, but it's still within the realm of possibility. A stunning demonstration of the destructive power of nature, the star's outer layers are ejected into space while its core is obliterated. The amount of energy released during the explosion is immense, briefly outshining the luminosity of billions of stars. As the explosion dies down, it leaves behind a luminous cloud of gas and dust, which grows and eventually fades into the interstellar medium. The effects of a Type Ia supernova can be far-reaching. When a white dwarf explodes, it releases material that is rich in heavy elements like iron and nickel. These elements are created in the last moments of the white dwarf's life and can eventually form new stars, planets, and even living organisms. In this way, white dwarf supernovae play an important role in enriching the universe with the building blocks of life. Although explosions are necessary for the evolution of galaxies, while the formation of new stars and planets is exciting, it also serves as a sobering reminder of the universe's inherent dangers. The fact that a white dwarf, a relatively peaceful star, can suddenly become a cosmic bomb shows how unpredictable the cosmos is. Even though we may be safe for the time being, the prospect of a nearby supernova in the future is real and unsettling. As for fast radio bursts (FBS), astronomers had detected some of the most intense and brief flashes of. One of the most fascinating aspects of fast radio bursts, FRBs, is that their origins are mostly unknown. This makes them one of the greatest unsolved mysteries in modern astronomy. What makes FRBs so terrifying is that they release more energy in that tiny moment, just a few milliseconds, than the sun produces in a whole day. Despite their brief duration, the power packed into a FRB is staggering, suggesting that whatever causes them must be an incredibly energetic event. The energy contained within these bursts is remarkable. In just a fraction of a second, they release as much energy as the sun emits in a full day. The events leading up to these bursts must be extraordinary, far more powerful than anything we have seen in our local cosmic neighborhood. This begs the disturbing question: are these bursts caused by exploding stars, or are they connected to? FBS have perplexed scientists since their discovery in 2007. The signals are not only rare, but also unpredictable, appearing suddenly from seemingly random spots in the sky. This makes it difficult for astronomers to pinpoint their exact sources. Unlike other cosmic phenomena, which can be studied over time, FBS vanish almost as soon as they appear. The energy involved suggests that whatever is causing FBS has the potential to destroy anything nearby. Despite the challenges, astronomers have recorded hundreds of FBS over the years, each one adding to the mystery of their origins. Several theories propose different sources for these powerful bursts, but one possibility is that neutron stars, and more specifically magnetars, are involved. Magnetars have magnetic fields trillions of times stronger than Earth's and can. Scientists are still trying to figure out what causes FBS. Some have speculated that black hole activity, like when two black holes merge, could be to blame. Mergers release gravitational waves, which we can now detect, but they could also release massive amounts of energy in the form of radio waves. But not all FBS fit neatly into this explanation, so other possibilities are being considered. Powerful bursts of electromagnetic radiation, including radio waves, if FBS are associated with such events, it would indicate that they're linked to some of the most destructive and violent forces in the universe. Collisions between black holes distort space-time and release vast amounts of energy. If this energy contains an FB, it would provide light on the kinds of catastrophic events that generate these signals. Another possibility is that FBS are related to star collapses into black holes, which occurs when a massive. There is a more speculative and potentially unsettling possibility that FBS are artificial in nature. However, when a star runs out of fuel, its core can collapse into a black hole and the outer layers are ejected in a supernova explosion. This abrupt collapse could produce a burst of radio waves that could resemble a FBRB. The intense burst would explain their short duration and high energy output, possibly produced by advanced extraterrestrial civilizations. Some researchers have speculated that FBS could be signals from faraway extraterrestrial technologies, such as powerful radio transmissions or energy sources. While this theory is still in its theoretical phase, the enigmatic nature of FBS does leave space for conjecture. For example, if a sophisticated extraterrestrial civilization were trying to communicate across the great distances of space, FBS could be a useful way to send out a signal that could be detected across billions of light years. The idea that FBS could be artificially created is intriguing and disturbing at the same time. If these bursts are signals from another civilization, what are they trying to convey? Are they intentional messages or the result of advanced technology that we don't fully comprehend? And if bursts are artificial, what does that say about the civilizations that create them? Are they much more advanced than us? We don't know when or where the next FRBS will appear, and each new detection raises more questions than it answers. Some FRBS seem to repeat occurring, which is unsettling. There is no concrete evidence to suggest that FBS are anything other than natural phenomena, but the possibility lingers in the background even without discussing the possibility of alien civilizations. Even though most FBS have come from faraway galaxies, The energy released in one of these bursts is so immense that even a nearby FFRB could have serious consequences due to the radiation from an FB. Some bursts appear multiple times from the same source, while others appear once and never again. This inconsistency adds to the mystery as scientists try to understand whether all FBS are produced by the same kind of event or if they have different origins entirely. Interactions with Earth's atmosphere have the potential to disrupt communications and damage satellites. In extreme cases, a very powerful burst could deplete the ozone layer and cause climate change. Scientists are studying FBS in the hopes of identifying patterns that will help them understand their origins. Recent advances in radio astronomy have led to the detection of more FBS than ever before. Previously, and as more telescopes go live, the predicted increase in burst detections is based on the fact that each new FB adds more information to the puzzle, allowing us to better understand the nature and origin of these mysterious signals. The discovery of FBS has ushered in a new era in cosmic science, and the brief but powerful bursts pose a challenge to our current understanding of cosmic-scale energy release, whether caused by natural causes or otherwise. Processes such as star collapses, black hole mergers, or even more exotic examples like advanced extraterrestrial technology serve as a sobering reminder of how little we know about the universe. Their unpredictable nature and immense energy are a reflection of the universe's power and mystique, and they leave us with the unsettling prospect that there are forces operating in the cosmos that we have not yet comprehended. An enigmatic and possibly hazardous area known as the orbit cloud exists, distinct from the well-known orbits of planets and asteroids in our solar system. This spherical shell of icy bodies extends nearly a light-year from the Sun, far beyond Pluto's orbit. Rather than being a singular object, it is a huge collection of billions, if not trillions, of icy remnants from the early solar system. It's a faraway, frozen sea of potential dangers that could. This asteroid cloud poses a significant danger to Earth's biosphere because it has never been directly observed. Its objects are too small and faint for even the most advanced telescopes to pick them up. Nevertheless, scientists are certain that it does exist because of the paths taken by long-period comets, which travel deep into our solar system before re-entering outer space after brief periods of proximity to the Sun. The Oort cloud, a gigantic spherical shell that encircles the entire solar system and contains innumerable icy bodies of varying sizes, is thought to originate in a faraway icy reservoir and is believed to be the source of these unusual and occasionally dangerous visitors. Its size is hard to fathom, but it is estimated to start at a distance of 2,000 to 5,000 times farther from the Sun than Earth and extends out to approximately 1,000 astronomical units or about a quarter of the distance to the nearest star Proxima Centauri. Rocks to comets that could be tens of kilometers across. These objects are relics from when the planets were still young and have spent billions of years in a faraway region, barely touched by the Sun's gravity. The Oort cloud poses a threat due to its instability. While most of its icy inhabitants maintain stable orbits far from the Sun, occasionally they are disturbed. Disturbances can be caused by many things, including when celestial bodies such as stars, the Milky Way, and interstellar objects interact with our solar system. It can cause perturbations that knock icy bodies in the Oort cloud out of their faraway orbits and send them hurtling toward our inner solar system. Once a comet from the Oort cloud begins its journey toward the Sun, it can take millions of years to reach Earth. These long-period comets are distinct from the shorter-period comets with which we are more familiar. The most concerning part about comets like Hearst Comet, which circles the Sun every 76 years, or cloud comets, is their size and velocity. Some only make one trip to the inner solar system before exploding into space, while others are captured into orbits that bring them closer to the Sun more often. If they were to crash with Earth, they could cause catastrophic damage. The most well-known example of an impact from a celestial object is the asteroid impact from a comet, which can travel at speeds of up to 70 kilometers per second, would release enormous energy, possibly triggering widespread extinctions and altering the climate on a global scale. This is in contrast to near-Earth asteroids, which astronomers are able to predict with some degree of certainty, and the 66 million years ago impact that wiped out the dinosaurs and caused massive global destruction. Observing and forecasting cloud comets is incredibly challenging. These objects originate from such vast distances that we don't usually notice them until they're almost at the sun, leaving us with little time to respond. While some comets are identified years in advance, allowing us to study their trajectories, others may approach abruptly, giving us only a few months or weeks of warning. The unpredictable nature of cloud comets makes them a significant natural hazard to Earth's biosphere, along with their potential for comets, whether in a descending or ascending trajectory, present fascinating scientific opportunities. These icy bodies have changed little since their formation, making them some of the oldest objects in our solar system. By studying comets, we can learn more about the early solar system, which in turn helps us understand the formation of planets and the possible delivery of life's building blocks to Earth. In fact, some scientists even think comets brought water to Earth. In spite of comets' scientific importance, we must not overlook the dangers they pose. A large or cloud comet's impact could cause catastrophic effects comparable to, or even worse than the asteroid that exterminated the dinosaurs. The impact would generate a huge crater, spewing out tons of dust and debris into the air, some of which could obscure the sun's rays for months, if not years. Efforts to detect and track comets from the Oort cloud are ongoing, but the sheer size and distance of this region make it a daunting task. The impact itself would cause widespread destruction with shock waves, tsunamis, and wildfires ravaging the planet. However, advances in technology, such as the development of more powerful telescopes and space-based observatories, may help scientists better monitor the outer reaches of the solar system in the future. There are a lot of factors that can affect a comet's trajectory, including the gravitational pull of planets, the sun, and even other stars. Therefore, it is difficult to observe or track comets over long periods of time, and our current ability to predict and defend against or cloud comets is limited. Another challenge is that, unlike asteroids, these comets often have extremely elongated orbits, which only bring them close to the sun very rarely. Despite the risks posed by the Oort cloud, scientists have proposed theoretical defenses against incoming comets, such as the use of nuclear explosives or kinetic impactors, which could divert a large, fast-moving comet from Earth. However, these methods are still in their early stages, and there is no guarantee that they would be effective against a comet of this size and velocity. This region of the solar system is both enigmatic and intriguing. It marks the extreme edge of the sun's gravitational pull, a faraway and frozen frontier teeming with frozen artifacts from the formation of the solar system. These icy bodies, although potentially dangerous, are also remnant from a time before Earth's existence, providing insight into the processes that shape the planets and the sun-planked stars. The collapsed specters of the universe are among these cosmic remnants. The most inexplicable and theoretical concepts push the limits of our comprehension of space and time. One such concept is the idea of Planck stars. If these hypothetical objects do, in fact, exist, there would be a significant change from our usual conception of black holes, which are thought to be the collapse of matter under tremendous gravitational forces. A less catastrophic result could be observed if stars collapsed at their cores. These objects would be extremely dense, but they could be able to avoid singularity formation by attaining a level of density where quantum gravity effects become noticeable, a state called Planck density. The concept of a Planck star originates from the meeting point of quantum mechanics and general relativity, two branches of physics that have not always been compatible. General relativity explains how large-scale gravity governs the motion of. Planck stars are believed to be the product of this convergence, where quantum gravity effects prevent a complete collapse into a singularity. This is what makes Planck stars so intriguing and potentially dangerous, unlike in most cases when quantum mechanics deals with the tiny particles that make up the universe. In such extreme conditions, like when matter collapses under the intense gravity of a black hole, these two realms must somehow converge. Due to their extreme compactness, black holes can collapse to a singularity, where their gravity becomes inescapable beyond a certain boundary called the event horizon. On the other hand, Planck stars don't collapse to a singularity. Instead, they compress to an incredibly dense but finite size. Despite this, Planck stars still exert a tremendous gravitational pull, but they don't have the infinite density or strange physics of a singularity. This could theoretically lead to, although Planck stars are less unstable than black holes, their enormous gravitational pull would still pose a threat to their environment. What's more unsettling is that, unlike traditional black holes, which emit radiation at their boundaries through processes like Hawking radiation or the accretion of nearby matter, Planck stars may not emit any radiation at all. This means that a Planck star could be roving through the galaxy, hidden from view. Planck stars are theoretically dangerous because they can travel through space undetected until they suddenly exert their gravitational pull on nearby objects. This pull could be catastrophic, causing planets to be pulled out of their orbits, moons to be torn apart, and stars to be disturbed from their stable positions. In contrast, black holes are usually found at the centers of galaxies or as remnants of larger objects. Planck stars, if they do in fact exist, could form in different ways than black holes. Their formation could be influenced by more subtle quantum effects, which don't follow the same predictable path. As a result, Planck stars could exist in unexpected places, floating around the galaxy like invisible wrecking balls. The concept of Planck stars adds another layer of complexity to our knowledge of gravity and collapsed objects. Collapse is due to its own gravity after running out of nuclear fuel, eventually creating a singularity where the laws of physics break down. However, in the case of a Planck star, the collapse stops before reaching this extreme state, creating a hyperdense object that is still governed by quantum mechanics. In this scenario, the Planck star would still have immense gravity, but without the infinite compression associated with a singularity. This situation raises profound questions about the nature of space, time, and matter at both the smallest and largest scales. On the grandest scales, the core of the Planck star concept is the theory of quantum gravity, which is still a mystery to scientists. This theory aims to explain the operation of gravity at the quantum level by integrating the findings of quantum mechanics with the gravitational forces outlined by general relativity. However, as of now, there is no comprehensive theory of quantum gravity. Planck stars may provide a glimpse into its potential operation. What happens when matter is compressed to the point where our understanding is limited? Planck stars suggest that there may be more types of collapsed objects in the universe than we think. Black holes have been the talk of the town for decades, but Planck stars represent a different class of objects that form under slightly different conditions. These ultra-dense objects could be impacting our universe in subtle but significant ways. Planck stars pose a significant threat to our current understanding of physics. If they really exist, they cast doubt on the long-held notion that black holes always produce singularities, and instead propose that quantum effects might establish a natural limit to the amount of matter that can be compressed. This finding has the potential to reshape our conception of star life cycles and the ultimate destiny of matter in the universe. And it may even inspire us to reevaluate the function of quantum mechanics in cosmic scale calculations. The finding of a Planck star would be a game-changer for science, giving conclusive proof of the existence of quantum gravity. This finding could pave the way for new areas of study in physics, enabling us to probe the boundaries of matter and energy in ways we can't even begin to fathom. On the other hand, there are concerns that Planck stars may be as elusive as they've been described, which could lead to catastrophic cosmic-scale catastrophe. Blazars, cosmic death lasers, powered by supermassive black holes at the centers of faraway galaxies, are objects so powerful and dangerous that they dwarf anything we can imagine. They lurk in the distant reaches of the universe, far beyond our solar system and the Milky Way. A nearby Planck star could destabilize entire star systems, wiping out planets and stars in their vicinity. Blazars, an extreme variation of quasars, are among the most energetic and brilliant objects in the universe. However, blazars are laser-like in their targeting. They shoot charged particle jets at Earth at nearly the speed of light. At the center of every blazer is a supermassive black hole. Black holes that are millions or even billions of times the mass of the Sun, and they're constantly devouring everything in their path. The material from the surrounding galaxy, including gas, dust, and other elements, falls towards the black hole, creating an accretion disk. This disk becomes extremely hot and releases massive amounts of energy, visible from great distances. However, what truly sets blazars apart is the fact that the black hole also releases relativistic jets, which are narrow streams of charged particles blasted out from its poles at nearly the speed of light. These jets are the source of the black hole's terrifying gravity. A blazar's radiation can outshine the entire galaxy it originates from, and the immense energy it carries allows it to travel millions of light years with little power loss. When one of these jets aims directly at Earth, it can be detected as a very bright source of radiation visible across multiple wavelengths, including radio waves and gamma rays. However, the true threat comes from the fact that these jets aren't just light. Relativistic jets are streams of high-energy particles traveling at almost the speed of light. They can destroy anything in their path. If one of these jets were to collide with Earth, the effects would be catastrophic. The radiation and high-energy particles would overwhelm Earth's atmosphere, damaging the ozone layer and exposing the surface to dangerous levels of radiation. Aside from disrupting communications, satellites, and electronics, the most critical consequence would be the intense radiation from a bizarre jet could harm Earth's biosphere and perhaps trigger mass extinctions. In the worst-case scenario, a direct hit from a bizarre jet could wipe out all life on a planet. What's more disturbing is that our understanding of why some black holes produce these jets and others don't is still in the dark. Most large galaxies, like our Milky Way, are. It is believed that some of these black holes contain one at their core, but only a tiny percentage of these actually emit the focused relativistic jets seen in blazars. The exact process by which black holes undergo this transformation is unclear, as is the duration of these jets. In some instances, blazars seem to cycle on and off, with the jets appearing and then disappearing. This raises the unsettling prospect that there may be a supermassive black hole lurking close to the Milky Way, patiently preparing to become a blazar and direct its destructive power towards Earth. The immense power of blazars is derived from the tremendous energy that is released when matter is pulled into black holes. As this material approaches the event horizon, the point of no return, it is accelerated to nearly the speed of light, which causes it to heat up and radiate energy across the electromagnetic spectrum. In certain instances, magnetic fields close to the black holes can concentrate some of this material into highly charged particle jets that shoot out from their poles. Energetic particles known as blazars are visible from billions of light years away due to their relativistic jets, which carry protons and electrons at relativistic speeds. Blazars are among the most powerful radiation sources in the universe, emitting energy across the entire electromagnetic spectrum, from low-energy radio waves to high-energy gamma rays. The latter are known to cause significant damage too. Though the thought of a Blaze BL's jet colliding with Earth is terrifying, there is some good news. The closest known Blaze BL is millions of light years away, well beyond the reach of any potential threat. A gamma ray burst from a Blaze BL could potentially penetrate Earth's atmosphere, causing mutations and DNA disruption, as well as radiation that could trigger atmospheric chemical reactions that would deplete the ozone layer, exposing living organisms to even more dangerous ultraviolet light from the sun. The unpredictable nature of blazars makes it difficult to predict when a black hole in a nearby galaxy will become active and begin feeding on new material. However, due to our limited understanding of what causes black holes to become blazars, we cannot rule out the possibility that there may be one much closer to Earth that hasn't been detected yet. Supermassive black holes are known to lie dormant for long periods of time before becoming active. This further adds to the terrifying nature of blazars. Although we have identified a handful, there may be many more dormant in faraway galaxies, ready to burst into action. Blazer jets are so intense and brilliant that they can be seen from great distances. However, it could take millions of years for us to detect them, meaning that distant blazers could strike us before we react. One of the biggest mysteries surrounding blazers is the role that magnetic fields play in creating them. Supermassive black holes are believed to have magnetic fields that can twist and compress as matter falls into their accretion disk, creating an effect similar to a cosmic slingshot that accelerates particles to almost light speed. These fields are extremely strong and assist in concentrating the jets into narrow beams that radiate out from the black hole's poles. The exact mechanisms underlying this process remain unknown, but scientists keep studying blazers in the hopes of discovering them. The intense light and radiation emitted by blazers provide astronomers with valuable insights into the processes that drive these jets and the extreme conditions close to a black hole's event horizon. By studying these objects, scientists are able to better understand the behavior of supermassive black holes, the impact of magnetic fields on the cosmos, and the basic forces at work that control the actions of matter and energy. Despite the threat they pose, blazers serve as a constant reminder of the vast power of the universe. Cosmic death lasers, driven by extremely massive black holes, are among the most extreme and violent phenomena in the universe. Their relativistic jets, which travel at almost the speed of light, are evidence of the tremendous energy that black holes can produce. Supernovae, which are stellar explosions that illuminate entire galaxies, are among the most spectacular and powerful events in the universe. At its core, a supernova is the death of a star, but it is a death that is accompanied by a tremendous explosion that can briefly outshine entire galaxies for a few weeks or months. The light from these explosions can be seen across vast distances, marking the final moments of a star that once burned brightly. This is a fascinating and important part of the universe's ongoing cycle of creation and destruction. In a matter of milliseconds, as a star depletes its nuclear fuel, the fine equilibrium between the outward pressure caused by fusion reactions and the inward pull of gravity starts to collapse in massive stars. This catastrophic collapse occurs when the star's core, which can no longer support its own weight, collapses in on itself. The collapse releases an immense amount of energy, which causes the outer layers of the star to explode outward in a blast that sends shock waves through space. The sheer magnitude of supernova is mind-boggling. In the span of a few seconds, the explosion can dissipate more energy than the sun will emit in its whole 10 billion-year existence. This dramatic burst of light causes the dying star to temporarily eclipse all other stars in its galaxy. Stunning as they are, the radiation they emit is both lethal and beautiful. Although most supernovae happen at great distances from Earth, the thought of one happening close by is terrifying. It's possible that our planet could be hit hard by the intense radiation, especially gamma rays, which could destroy the ozone layer that protects us from the sun's ultraviolet rays. This could cause extensive ecological damage and even mass extinctions. An explosion powerful enough to trigger changes in the orbits of nearby planets, disrupt the formation of new stars, and even alter the chemical composition of interstellar space can have far-reaching consequences for entire star systems, much like the event thought to have contributed to the extinction of the dinosaurs. The effects of radiation from a supernova are not limited to planets, though they can affect life on Earth as well. Stellar explosions, despite their destructive power, are an essential part of the universe's creation cycle. During an explosion, elements like iron, gold, and uranium are formed in the intense heat and pressure of a collapsing star. When the explosion is over, these elements are scattered across space, where they can eventually become part of new stars, planets, or even living organisms. Play a crucial role in the cosmic recycling process, which involves dismantling old stars and reassembling them with their remnants. This endless cycle of creation and destruction is one of the most basic processes in the universe. Stars are born, live their lives, and then explode, dispersing their material across the cosmos. The remnants of these explosions, which are clouds of gas and dust enriched with heavy elements, serve as the seeds for the next generation of stars. This process has produced the supernovae are a reminder of the dual nature of the universe. They are essential to the formation of the elements that make up planets and living organisms, but they also show how violent the universe can be. The explosions that create these elements can wipe out entire civilizations if they happen too close, so supernovae are a reminder of the galactic, stellar, and planetary systems that we know today. A Type 2 supernova happens when a star with a mass at least 8 times that of the Sun reaches the end of its life. These stars burn through their nuclear fuel at a much faster rate than smaller stars like the Sun, and when the fuel is exhausted, their cores collapse. In this cosmos, creation and destruction are inseparably linked. The death of a star is not the end, but the beginning, because the material that remains goes on to create new stars and planets. Type A supernovae happen in a different way. They happen when a white dwarf star in a binary system takes material from its companion star and eventually reaches a supernova explosion. In some cases, the star's core survives the explosion and collapses into a neutron star or even a black hole. The outer layers of the star, however, are ejected into space, creating a brilliant explosion that can be seen from far away. Supernova explosions can be classified into 2 types. Type IA, which involves the collapse of a smaller, more compact star, and Type 2, the collapse of a single massive star. Both types of supernova explosions release tremendous amounts of energy and can produce the heavy elements needed for life. The remnants of a supernova explosion, including the material ejected during the explosion, can remain for thousands of years. A supernova remnant is a beautiful cloud of gas and dust that lights up the sky with intricate patterns of glowing material. One famous remnant is the Crab Nebula, which was formed by a supernova that Chinese astronomers observed in 1054 AD. Even today, the Crab Nebula continues to expand its filaments of gas and dust, giving us a glimpse of the immense power of the original explosion. Supernovae also play an important role in the formation of new galaxies. Although supernova explosions are extremely rare occurrences on a cosmic scale, they are quite common on a human time scale, and the shock waves they produce can cause nearby clouds of gas and dust to collapse, resulting in the birth of new stars. In this way, supernovae have played a role in driving the process of star formation, continuing the creation and destruction cycle. With billions of galaxies in the universe and an estimated 1 supernova every 50 years for our Milky Way, these explosions constantly shake up space with their debris and propel the universe's ongoing evolution. Despite their devastating power, supernovae serve as a constant reminder of the universe's precarious equilibrium, teaching us that creation and destruction are inseparable, with each explosion playing a profound impact on the universe's galaxies, stars, and planets. Without these catastrophic occurrences, the cosmos would be considerably less dynamic, offering fewer chances for the creation of new stars and planets. In this sense, supernovae serve as a catalyst for cosmic creativity, ensuring that the cosmos is perpetually transformed and renewed. White holes, the theoretical analogs of black holes, are time-reversing celestial bodies that pose perplexing and unsettling challenges to our comprehension of the cosmos. While black holes are renowned for their capacity to draw in all matter, light, and time, white holes are thought to do the exact opposite, expelling all cosmic debris and energy with an overwhelming force. Despite this, no white holes have been observed. White holes are thought to originate from the same general relativity equations as black holes. Forecast black holes, which makes them an intriguing, though theoretical, possibility. Put simply, a white hole is an object into which nothing can fall, in contrast to black holes, which are characterized by their overwhelming gravitational pull. Once matter enters a white hole, it cannot escape. Instead, it is pushed out into space, creating a region where energy, radiation, and matter are ejected into space. If white holes really exist, they would be among the most violent phenomena in the universe. Theoretical physicists who study general relativity propose that white holes could be the time-reverse counterpart of black holes. According to them, White holes constantly spew material at tremendous speeds, causing shock waves and cosmic debris to be scattered in all directions. The energy released by these holes could be as powerful as the most powerful supernova, sending radiation and high-energy particles hurtling through space. Time seems to travel backward when a white hole is trapped, ejecting anything that gets too close. This peculiarity begs the question, could white holes be locations where time runs in reverse, undoing the processes that black holes initiate? It's just one of many ways in which white holes make us question our reality and make us wonder if time is stable and linear or if it can act in ways we don't completely comprehend. If white holes exist, they might imply that time can be changed or that it works differently in different parts of the cosmos. In this way, white holes bring a sort of philosophical terror. The idea that time can be turned backwards, that processes can be halted just as easily as they can be started, calls into question our entire notion of cause and effect. One of the most fascinating things about white holes is the potential connection to. For some, the white hole represents the last stage of a black hole's life cycle, when it releases all the matter and energy it has stored after absorbing it for billions of years. On the other hand, there's also the possibility that black holes eventually transform into white holes and explode violently, releasing all the matter and energy they have ever stored. The connection between black holes and white holes is even more profound. Some theories suggest that black holes could act as portals to white holes, allowing matter to be drawn into one region of the universe and then ejected by the other. This idea is related to wormholes, which connect faraway regions of the universe through space-time. If this is true, then black holes and white holes could constitute a cosmic recycling system, with matter being drawn into one and ejected from the other. Some scientists have speculated that a white hole could create an entirely new universe while simultaneously ejecting matter into our own. In this scenario, the matter and energy that falls into a black hole is compressed to an infinitely small point, known as the singularity. Another mind-bending possibility is that white holes could be responsible for the creation of new universes. Though it's a far-fetched theory, there's a chance that our universe may have originated from a white hole in another, larger universe. This would mean that both black holes and white holes could serve as cosmic portals to other realities. White holes, on the other hand, are still largely theoretical, while black holes have been observed due to their gravitational effects and the radiation released by the matter they devour. No proof of a white hole has been found so far. This doesn't mean they don't exist. It could be that they're rare, or that they're located in inaccessible parts of space, or that our current technology can't detect them under certain circumstances. Regardless, the concept of white holes makes us face some of the most profound cosmological concerns, which test our comprehension of the interplay between space, time, matter, and energy, while simultaneously testing the limits of our imagination and providing a glimpse into a cosmos where the rules we normally take for granted, like the march of time and the inevitability of black holes, may not always hold. For example, the violent outflow of matter and energy from a white hole would render it an object of tremendous power and unpredictability. Should one happen to be located near a star system, the consequences could be: a white hole's radiation can be so powerful that it sterilizes planets in its vicinity and makes them uninhabitable. Any star system unlucky enough to be in its vicinity would be bombarded with high-energy particles and radiation, creating a chaotic and dangerous environment. If white holes are linked to black holes, they can also cause devastating disruptions to planets' orbits, possibly removing them from their solar systems altogether or sending them hurtling into deep space. Symbolize the pinnacle of cosmic paradoxes, black holes, which are so powerful that not even light can evade their gravitational pull, and white holes, which are so weak that nothing can enter them and everything is ejected. These two things couldn't be more different, yet they could be connected in ways we don't yet know. The very idea of white holes adds another layer of mystique to the cosmos, and they serve as a reminder that our knowledge of space and time is still limited, and the cosmos could contain mysteries that are beyond our present comprehension. Neutron stars, the dense remains of supernova explosions, are among the most remarkable celestial objects. When a star as massive as the Sun dies, its core collapses under the force of its own gravity, becoming a neutron star. This object is so dense that a teaspoon of matter would be compressed into it. Neutron stars are the remnants of a catastrophic event where the usual laws of matter are strained to their absolute limits. Their density is so great that gravity crushes atoms, forcing protons and electrons to combine into neutrons. Despite their relatively small size, about 20 kilometers in diameter, roughly the size of a city, neutron stars contain more mass than the Sun compressed into a volume just a fraction of its size. Produces a stellar object composed nearly entirely of neutrons. The result is a densely packed stellar core, where even a small amount of matter, the size of a sugar cube, would be heavier than a mountain on Earth. The stellar core's tremendous gravitational pull would crush anything that got too close, creating an incredible force beyond anything seen in the normal universe. Stellar cores also bend space and time around them, much like black holes, but without the event horizon. Neutron stars are extremely dangerous because of their magnetic fields, which are trillions of times stronger than Earth's. When charged particles are trapped in a neutron star's magnetic field, they are accelerated to nearly the speed of light, producing radiation beams that can extend into space. These beams are occasionally visible as pulses from neutron stars that spin. Pulsars are both fascinating and dangerous objects. Pulsars transmit electromagnetic radiation in a precise rhythm, similar to a cosmic lighthouse sweeping across the universe. The radiation they emit has the potential to destroy any nearby planets by bombarding them with high-energy particles, eliminating any chance of life. In extreme cases, the radiation pulses can be so powerful that they destroy entire solar systems. To be detected from a great distance, hundreds or even thousands of light years away. The intense environment surrounding these neutron stars, which spin hundreds of times per second, is so powerful that anything that gets too close to them would be blasted with radiation. Any star systems unfortunate enough to be near an active pulsar could face disastrous consequences. One unexpected twist in the story of neutron stars is that they can keep spinning fast because the original star's angular momentum is conserved. In some instances, neutron stars spin so quickly that they complete one full rotation in a fraction of a second. These millisecond pulsars can spin hundreds of times per second, releasing radiation beams at regular intervals. Pulsars are among the most extreme objects in the universe, with forces so intense that they test the boundaries of physics and provide scientists with a unique opportunity to study. Neutron stars provide a one-of-a-kind opportunity to study the behavior of matter under extreme conditions. One of the most intriguing things about neutron stars is the information they reveal about the limits of matter. In neutron stars, the matter is compressed to unprecedented extremes, far beyond what happens in regular stars or planets. The neutrons inside the star are so densely packed that they create a soup-like mixture, blurring the boundaries between individual particles. This begs the question, is there a limit to the amount of matter that can be contained? A number of scientists have speculated about the existence of objects denser than neutron stars out of philosophical curiosity. One such object could be a quark star, which would form when the neutrons inside a neutron star are further broken down into their constituent particles quarks. In such a star, the matter would be compressed to the point where individual quarks would be squeezed to their smallest possible size. The neutrons have been superseded by a cosmic ray, Ca, of quarks, which are the building blocks of protons and neutrons. If quark stars did exist, they would be even denser and smaller than neutron stars, pushing the boundaries of our knowledge of matter to new heights. Another possibility is the existence of strange stars, which would be even more exotic than quark stars because they would be composed of matter that we have never seen before in the universe. These objects are still considered speculative at this time. However, These findings do show that neutron stars aren't necessarily the last chapter in the tale of collapsed matter. There may be even more unexplained forms of matter out there, just waiting to be found. Despite their extreme characteristics, neutron stars are vital cosmic laboratories. By studying them, we can learn more about the forces that govern the universe, including gravity, electromagnetism, and nuclear physics. Neutron stars are not only fascinating scientific objects, but they also serve as reminders of the violent processes that shape the universe. Each neutron star is the remnant of a supernova explosion, a catastrophic event that transformed matter into an extremely dense form. By studying this matter in such an extreme state, we can learn how particles behave under conditions that cannot be replicated on Earth. This, in turn, helps to push the boundaries of physics. Neutron stars are formed when a massive star explodes, releasing heavy elements such as iron and gold into space. These elements then go on to form new stars and planets, including Earth, which can support life due to its extreme properties. So, neutron stars aren't simply the debris from a star's demise. They're an integral part of the universe's creative cycle. Neutron stars are a common occurrence in the universe and are believed to number in the millions. They are small and faint, making them difficult to detect. The ones that are visible, like pulsars, provide a glimpse into the immense forces operating inside these objects, but they are only the tip of the iceberg. Many neutron stars are probably floating through space undetected, their powerful gravitational poles and magnetic fields hidden from view. Neutron stars are fascinating to scientists and serve as a reminder of the vast. Neutron stars are dense remnants of massive explosions that tested the limits of matter and gravity. They pose a challenge to our current understanding of physics by providing a window into a world where the laws of physics do not apply and make us wonder if there are more extreme objects out there. Whether they pulsate with deadly radiation or quietly drift through space, neutron stars are a testament to the incredible forces at work in the universe. Form the cosmos, representing the power of both destruction and renewal. I hope you liked the video, and if so, please subscribe. Thanks for watching.